Hi, my name is Thomas Winters, and in this work we present DeepStochLog, a framework for neural-stochastic logic programming. More concretely, we introduce neural definite class grammars by introducing neural probabilities in a rule of stochastic definite class grammars to create DeepStochLog, a scalable, state-of-the-art framework for neural-symbolic tasks. As the name suggests, it's a little sibling of DeepProblog, which combines probabilistic logic with neural networks. DeepStochLog, on the other hand, uses a different semantic, namely stochastic logic programming, making it more scalable. The most fundamental contribution of this work is the introduction of the neural definite class grammar. To understand this, let's first look at the most basic grammar type, namely the context-free grammar. Here you can see a simple context-free grammar example that parses sequences that represent sums of digits. A grammar consists of expansion rules, some of which share the same head to represent a choice point. The non-terminal e can map to either n, which maps to digits, or to another e expression plus a digit. Context-free grammars are widely used for modeling context-free languages, as they are great for quickly determining if a given sequence is part of this language or not. It's also great for marking elements of a sequence with a specific tag, for example, part of speech tags for NLP applications. Also, generating all possible elements of a language or generating an infinite sequence of them if the grammar is recursive is another application field of context-free grammars. A popular extension to context-free grammars is probabilistic context-free grammars. They add probabilities to the expansion rules, which allow to calculate the probability of a sequence to be generated. Since the expansion rules with the same non-terminal as head represents a choice point, the probabilities of all expansion rules with the same head must sum to 1. By following the path from the start symbol to the total derivation, we can multiply all of the probabilities to find the probability of a sequence. For example, here, the probability of the sum of 3 digits being generated has a probability of 0.01%. If the grammar is ambiguous, that is, if a sequence can have multiple derivations, these probabilities allow us to determine what is the most likely parse for the sequence of the terminals. Another extension to context-free grammars is definite class grammars, which add logic to context-free grammars. It's a popular way for modeling grammars in the logic programming language Prolog. In this running example, you can see that through argument unification, the logic part between the curly brackets, we can calculate the sum of the expression. Thanks to this logic power, DCGs can thus model more than just context-free grammars, but also context-sensitive and even higher. So what happens if we extend definite class grammars with probabilities, just like we did with the probabilistic context-free grammars? Well, that's what we call a stochastic definite class grammar. And this is similar to how a probabilistic context-free grammar adds more capabilities to context-free grammars. Here, we can also calculate the probability of a certain sequence. However, one important thing to note is that the probabilities of all these sequences in the languages do not have to sum to 1 anymore. This is because there are derivations that are possible that are failing when the unification of arguments is impossible. But these derivations still carry some probability. And that means that there is a loss of probability mass. So now that we have this stochastic definite class grammars, we can apply the same trick that DeepProblog applied to probabilistic logic, namely swapping out the probabilities with neural probabilities. A neural probability is a neural network outputting a probability that is being used by a logic rule, or in our case, a stochastic definite class grammar expansion rule. This extension allows the framework to not only deal with symbolic inputs such as strings, but also with subsymbolic inputs, such as images, or just images of these digits in this case. The neural network processes the images and then predicts a probability for all elements of a given domain. It is also a form of learning rule probabilities using neural networks from these neural probabilities. So these neural definite class grammars are the main power behind DeepStochLog. Due to its simple semantic for calculating probabilities, it allows us to solve many neural-symbolic tasks very efficiently. So here you can see the definition of such a neural definite class grammar rule. It allows the expansion rule to have an atom as its head of the class, thus allowing non-terminals to have arguments to unify. The expansion of the rule is a conjunction of goals G1 to Gn, which can be other atoms or any other logic programming component. Then for the neural probability, NN, there is a neural network M having inputs I and outputs O, which are variables occurring in the expansion rule to the right of it. All output variables O are also constrained by their corresponding domain D. The neural network M then maps a probability distribution over all possible output domains O. So, how can we perform efficient inference on these neural definite class grammars? To explain this, we can first look at how derivations work in stochastic definite class grammars. You can see here that each time a non-terminal is expanded, we save the probability of this expansion rule and then also save the unifications that occur, such as n1 with the number 2. For neural definite class grammars, we cannot make any assumptions about the content of the subsymbolic elements such as the images. As such, the possible derivations with neural probabilities contain all possible domain elements according to the rules. For this, we prove the derivation given at the input sequence. For example, if we know that the sum is 1, the digits could be either 0 plus 1 or 1 plus 0. Both branches have to be considered if we want to know which one is most likely, or if we want to know the complete probability of all possible derivations in this given sequence. Using Prolog, we can then calculate the proofs and keep track of them in a classic AND/OR tree. We can then use this AND/OR tree to perform all kinds of inferences by applying different semirings to them. For example, replacing the ANDs with multiplications and the ORs with summations, we find that the total probability assigned to the goal is, in this case, 0.11. By replacing ANDs with multiplications and OR with maxes, we can find the most likely derivation, in this case 0 plus 1. But as you can see, the left branch has more probability, will be found as the most likely parse, but we also need to still keep track of the right branch if we want to know the total probability of this sequence. Apart from the fact that these probabilities don't require large knowledge compilation like the probabilistic logic semantics require that is used in DeepProblog, we also optimized inference using multiple tricks. So we use SLG resolution instead of SLD resolution, which stables the returned proof trees, thus reusing a lot of the computation when calculating the total probability. We also batched network calls, where all calls to a particular neural network are delayed and done all at once. So how do we learn in DeepStochLog? Well, the leaves of a DeepStochLog AND/OR tree are all probabilities or neural probabilities. DeepStochLog just links these predictions together and uses them to calculate a loss. The loss is being minimized with respect to these neural probabilities P, as seen in the formula here on the slides. In many ways, DeepStochLog is like DeepProblog, but for stochastic logic programs. Here you can see the difference in the main extension that both frameworks do to their respective probabilistic logic framework. DeepProblog adds neural predicates, DeepStochLog neural grammar probabilities. DeepStochLog is faster to perform inference tasks on thanks to the simpler SLP semantics. It assumes no disjoint sums and can simplify many calculations. Problog, and by extent DeepProblog, deal very well with this disjoint sum problem, which are thus more expressive but at the cost of requiring a large knowledge compilation step. However, most real problems do not require these expensive semantics and can get away with the tools provided in DeepStochLog. One way to understand the difference in this probabilistic versus stochastic logic programming is that PLP is much like performing inference on a weighted graph where random graphs are sampled from, and SLPs is similar to sampling a random walk in such a weighted graph. We performed several experiments to answer 4 research questions. We wondered if DeepStochLog was able to achieve state-of-the-art performance on neural-symbolic tasks. We wondered if it was indeed faster than other neural-symbolic frameworks, and if the SLG tabling really mattered for this. We wondered if DeepStochLog can handle large-scale tasks, and if it can handle larger-scale tasks than other frameworks, and whether or not DeepStochLog is limited by its grammar-like structure and notation, or whether it can encode more general programs. We created 6 different tasks and found that it does achieve state-of-the-art performance, is faster than DeepProblog and comparable frameworks, and can handle larger programs because of that. So here you can see 2 first tasks which are predicting about the outcome of handwritten mathematical expressions. The first one just sees a sequence of images, and then what the sum of the images consisting of these MNIST digits are without knowing the individual labels. In the second one, also the operators like plus, minus, and times are encoded in the images. We see here that DeepStochLog is able to handle larger expressions and with better performance. The fact that DeepStochLog can handle longer sequences is due to the fact that these inference times are much slower and don't explode like the other frameworks for large sequences, as can be seen in this table. Tasks 3 and 4 are about classic grammar problems, but using MNIST digits as terminals to encode these sequences. Task 3 is all about parsing well-formed parentheses, where a 0 represents an open bracket and a 1 a closed bracket. The training data only consists of valid sequences, but without any labeled parses. The task is to predict the parse given a sequence of images by taking the most likely parse. Task 4 is all about distinguishing two languages that are modeled as a context-sensitive language, all using 3 numbers of the alphabet. Given a sequence, it has to predict whether the 3 numbers all occur equally often next to each other, or if they do not. So, if for example AACCBB would show up, then that will be class 0, or if AAACBB, that would be class 1, since not all of them occurred equally often. We can see that DeepStochLog handles these longer sequences better than DeepProblog. Not only that, but it's also more natural to express these problems in DeepStochLog thanks to its grammar-like syntax. Here you can see the program encoding the background knowledge of the well-formed parentheses, and here the one representing the A to the N, B to the N, C to the N language disambiguation. We also evaluated its performance on a real problem where scientific papers that are linked with a citation graph have to receive a certain label, but only very few of the papers actually have a label. While other solutions to the problem require a lot of problem-specific models, DeepStochLog can handle this without further modification. A more general neural-symbolic problem is encoding natural language text describing an algebra problem. For example, Mark has 6 apples, he eats 6 and divides the remaining among his 2 friends. How many apples did each friend get? A trick to encode this in grammars is by allowing a rule to expand to an empty body. This way, no part of the sequence is consumed by the rule, and then we can apply pure logic there. We can thus consume the whole sentence as one token and then embed it using an RNN. This empty body trick shows how we can translate a general program to our semantic. It allows a fairly straightforward translation from DeepProblog programs to DeepStochLog programs. So for example, here you can see how the DeepStochLog implementation is compared to the DeepProblog implementation to the left of it, and how it was derived. You just need to add some domains and some uniform probabilities to make sure it is following the correct SDCG syntax. There are several things we would like to add in the future. We would like to add some syntactic sugar to allow for structural learning, similar to Prism-like switches. We would like to support calculating the true probability, which accounts for the loss probability due to failed derivations, and some larger scale experiments, for example, on Clever. Comparing with more neural-symbolic frameworks would also be very nice, and we would also like to see how it performs in a generative setting, as these grammar-like structures and generative neural networks and the increased performance of this framework lend itself very well for these generative tasks. So all in all, we presented DeepStochLog, a state-of-the-art neural-symbolic framework for stochastic logic programming, and I would like to thank you very much for watching this presentation. The code of DeepStochLog is available on the following URL, and the framework itself can be easily installed for using Python by calling pip install DeepStochLog. If you're interested in any of our follow-up research, feel free to follow us on Twitter on the Twitter handles down below. And thanks again, and I hope to see you on the conference very soon. Thank you very much.